Alright, 8.7, fitting to a normal distribution. You're going to want to copy this to the top of the paper I handed you. So go ahead and copy that to the top. This is the only thing you have to copy up there. Except maybe a few extra notes I might write. Alright, so there's what's called the normal curve. Sometimes people call it the bell curve. And basically, a lot of times in real life, in real life statistics, people tend to plot their data as what's called a histogram. It kind of looks like a bar chart, but the bars are touching. And what happens is they draw or they create these graphs, and the shape takes on the graph takes on a certain shape. And if you were to connect the tops of each of these bars, like putting a dot at the top, and then connect it with a curve, you get what's called a bell curve. The bell curve is such a common occurrence in real life statistics and even theoretical statistics that it has a lot of its own special properties. And we're going to talk about a few of those properties for a moment. These are properties you're going to want to make notes of. The first thing is, this is not the x-axis. This is an axis, but it's not the x-axis like you normally know it. It's what's called the z-axis. So that's why I label it z. The bell curve is symmetric about what's called the mean. You know the mean. Now, you learned that the mean has a symbol. Remember you learned x bar is the mean? But actually, x bar is the mean when you have a sample. And we didn't talk about that yet, so that's actually a new thing to you. But x bar is the mean when your mean's part of a sample. But when your mean is for a population, we use the Greek letter called mu. Like the sound a cat makes. Mew. Yeah. So the bell curve is symmetric around the mean, meaning that if I took this part and folded it over the dotted line, it would fit perfectly. Also, each unit is not one unit like the number line. Well, it's a unit, but it's not like 1, 2, 3. Each unit is a standard deviation. Remember, standard deviation is sigma. So as I go from the center of the curve to this unit right here, this is one standard deviation. From here to here, it's 2 standard deviations. So that's why each of these is marked with mu plus sigma, mu plus 2 sigma, and so on. Now, in the other direction as well, it's mu minus sigma. We never go beyond 3 sigmas because, well, I'll tell you why in a second. Basically, what we're doing in this section is we're going to be finding area underneath the curve, between the curve and the z-axis. For example, we may be finding an area such as this. And I'm going to shade it in to show you that this may be an example of an area we may find. Now, this has some area, and this area, I want you to make a note, this area will always be less than 1. Because the area underneath the entire curve, and by the way, this curve does go on forever in both directions. The area underneath the entire curve is equal to 1. So entire area is equal to 1. Which makes sense now that if I took a portion of the area, not the entire thing, but just this portion, it should be less than 1. Another property is the curve goes on forever in both directions. So you could say the domain is all real numbers, although you don't need to know that. Don't write that down. But it goes on forever both directions. And actually, the curve never crosses the z-axis. It gets infinitely close. We did learn that has a word, which means that this is asymptotic. Remember, it gets infinitely close, but never touches the z-axis. It just gets infinitely close as time goes on in both directions. Why does that matter? Because that's the reason why we don't go more than 3 standard deviations on the z-axis. If I was to go a bit further and go to mu plus 4 sigma, if I was to find an area like over here, like shade this in, that area is so small, it's basically 0. So that's why we don't ever go beyond 3 standard deviations in either direction. All right. So what we're going to be doing in this section, I want you to keep in mind, is we're going to be finding area. That's the main idea in this section. And finding this area, it's the same thing as finding probability. Let's actually make a note of that as well. I'm going to use a different color. Finding area is the same thing as finding probability. Okay? One last thing I'm going to show you before we do the examples together is we're going to be using, and you're going to be getting a copy of this yourself. And it'll be front and back when you get it. But we're going to be using this z-score table. Now it looks really confusing. Maybe I'm gonna assume it looks confusing to you, but I'm gonna show you how to read it. It's actually pretty easy to read because you're not gonna need every number at once. You're actually gonna be only looking for one or maybe two numbers in a problem. And I'll show you how to do that in the middle of the problem, but we're going to be referencing this in a moment. Let's go ahead and go to example 1, part A. Your paper that you got from me says, scores on a test are normally distributed. By the way, it's such a key phrase. Normally distributed is such a key phrase. Like, on your paper, I want you to underline that right now. Oh, sorry, I didn't realize it was fuzzy. I want you to underline normally distributed right now. This is such a key phrase. If you see this, you're probably using the z formula. Z equals x minus the mean divided by the standard deviation. So keep that in mind. These are about the same thing. All right, there we go. So what I want to do is I want to identify the mean is 75, which means that mu is 75. The standard deviation is 8, sigma equals 8. And what we're trying to find is we're trying to find p of x is less than 87. That's what this says in algebraic terms. Well, what we're going to do is we're going to convert this x value, this raw data score, into its corresponding z-score. So let's go ahead and do that now. We're going to plug in x, mu, and sigma. We know all three of those. X is 87, minus the mean, which is 75, divided by the standard deviation, which is 8. We're going to get out our handy-dandy calculator. 87 minus 75 is 12. Divided by 8 is 3 halves, or let's actually say 1.5. So what happens is this converts into p of z is less than 1.5. So this is what we're really trying to find. What I recommend at this point now, what I recommend here, is to draw a simple curve. It doesn't need to be as detailed as the one I drew on the other paper, but we're going to go ahead and just label it like this. And what we're trying to find is the probability of z being less than 1.5. Where's 1.5 on the z-axis here? It's right here. And what I want you to do is find that number, and you're going to draw a line from the number up to the curve like this. Now, I want you to think about z is less than 1.5. If you were to shade an area that represents that, what side would you shade? Would you shade this side of this line that you just drew, or this side? Well, it says z is less than 1.5, so that means what you're trying to find is the area to the left of 1.5, and you got to remember that this area does go on forever. But how do you find that area? How would you even know how to find that? That seems very complicated. It's not like a nice rectangle or something. So how would you find the area? That's where this table comes into play. Again, you don't have this yet. You'll be getting your own copy soon. But the way to find it is, if we're trying to find the probability of z being less than 1.5, what this table tells you is it tells you the area to the left of the z-score. So let's go ahead and find 1.5. That's what we're trying to find. What you do is you start with the left side of the table, or if you're on the other, oh sorry, it is on, okay. We want positive 1.5. If you look at all these z-scores, these are all negative. So I'm going to go to the other page. So I'm going to make a note. These are all my negative z-scores. Again, you'll be getting your own copy. These are all my positive z-scores. Now, my z-score is positive 1.5. What I do is I look to the left side first. I find 1.5 right here. So we're going to be on this row. Now, 1.5 is really 1.50, right? That's important to know. Because this row on top in bold right here determines the 100th place. So 1.5 and 0 meet right here at this column in this row. So that area is 0.9332 right here. And so that's my answer. I'm just going to reiterate that one more time. All these numbers give area, the area to the left of your z-score. Let's do part B. Let's find the probability of scores between 71 and 75. So 71, what this looks like in terms of the P of X notation, that's what we're trying to find. We need to convert these to their corresponding z-scores. So let's go ahead and do 71. To find its z-score, we do 71 minus the mean, which the mean was what, 75? Divided by the standard deviation. 71 minus 75 is negative 4 over 8, and that's negative 0.50. So I'm going to put that right here. And X becomes Z. Now let's go ahead and find 75's z-score. So I do 75 minus the mean, which is 75, over 8. I think you can see what's going to happen here. 75 minus 75 is 0 over 8, which is just 0. It's okay to get 0, by the way. So let's think about what's going on here. Let's go ahead and draw another bell curve. So we have 0, 1, 2, 3, negative 1, negative 2, negative 3. And what are we trying to find? Well, let's go ahead and mark both these points. Negative 0.5 is right here. 0 is right here. So I have to draw 2 lines for this problem. The other one, I only drew 1 line because I was only trying to find, I only had 1 number involved. So we're trying to find this sliver right here. All right, so it's a little more complicated when I have 2 numbers that I have to do. What we have to do is we have to find the area of the right side first. So I want to find the area that's to the left of 0. So I'm going to look up 0 on my z-score chart. If you look right here, z equals 0 is right here. So 0 is really 0.00. If you look at what that area is, it's 0.50. So for 0, the area is 0.5000. Now let's look up negative 0.5. Well, I don't want to use this z-score side. It's a negative number. So I go here. Now negative 0.5. That's going to be all the way, I don't know if you can see that, sorry the lighting, but negative 0.5 is right here, but I need negative 0.5, 0. So that's negative 5.9, this is negative 5.8, so I have to go all the way over here, negative 0.50. So I'm in the last column, and I'm about right here, so 0.3085. So that's that area. 0.3085. So let's think about this real quick. If I want to find this area, think about if I wasn't restricted on this line right here. That means the area would go to the left forever, from 0 to forever. What would that area be? It would be 0.5000. But now I need to subtract out this white area right here. What is this white area? That's this number. So basically the trick is do the bigger probability minus the smaller one. If we do that, we get 0.5000 minus 0.3085. And we get, as a decimal, 0.1915. See if you can try out part C real quick. See if you can try it out on your own. Pause the video. It's the same mean and standard deviation. And I'm going to go through this one quicker for the sake of time. Alright. So maybe you pause it to see if you could try it yourself. Maybe you didn't, if you lazy or something. We're trying to find the probability of 67 is less than X is less than 91. We need to convert these to their z-scores. So for 67, we do 67 minus 75 divided by 8. Which is negative 1. I do 91. 91 minus 75 over 8. 91 divided by, sorry, not divided by, minus 75 divided by 8, which is 2. So what we're really trying to find is the probability of being between negative 1, z, and 2. So let's go ahead and just draw a quick sketch of what this looks like. 0, 1, 2, 3, negative 1, negative 2, negative 3. So I'm at negative 1 and 2. I'm going to draw a line here and a line here. So the area I'm trying to find is this. All right, so we're going to look up these two numbers. Let's find negative 1's area and 2's area. So I get out my table. Let's start with negative 1. I need my negative z-score. So negative 1 is really negative 1.00. So I'm going to look at this row and the last column. So they meet at point 1587. For 2, it's really 2.00. Sorry, I know that's really fuzzy. Okay, there we go. That would be 0.9772. And then you just subtract the bigger area from the smaller area, and that's going to give you this area right here. Let's just calculate it real quick. Minus 0.1587, and we get 0.8185. That's our area. So there you go. And so they call this the normal curve, right? Here's my joke, by the way. You can stop if you want to, but here's your normal curve. Then you know what this is? This is your paranormal curve. I'm sorry. It looks like a ghost, right? That's what it looks like. That's what it's supposed to look like. Anyways, thank you guys, and there you go.